Hey y'all, Dawe here. I'll be presenting on the fourth lab of Introductory Physics to at Georgia Tech, titled Magnetic Braking with Faraday. The purpose of this experiment was to collect observational data regarding a magnet falling through a conductive, non-ferrous tube of aluminum, and using a computational model to model this interaction, and then comparing what was predicted with what was observed. And for a preview of the main results, the average time for the magnet to fall through the tube was found to be 0.662 seconds, while the time to fall through the simulated tube at a reasonable time was 0.25 seconds. The approximated magnetic dipole that matched the observed time to fall through the tube was 0.678 ampere meters squared. Shown here are the models and physical principles employed in this experiment. Magnetic flux refers to the total magnetic field that passes through a given area, while the magnitude of the electromotive force, EMF, is proportional to the rate of change over time. The central question in this experiment was what was the force on the falling magnet due to the induced current loop from the tube of foil. Now, the magnitude of the magnetic force on the loop would be equal to the magnitude of the force on the magnet by the loop, only opposite in direction. The force on the loop was deemed to point downwards, while the force of the loop on the magnet was upwards. Since the y components of the force were the same around the loop, the total force became the circumference of the total loop multiplied by the magnetic field of the magnet and the cross product between the magnetic dipole moment and b hat vector. Here are the relevant physical parameters and average times for the pass-throughs, and the alignment of the magnet was shown to not affect the rate at which the magnet was passing through the tube, or its time to pass through. Shown here are additional parameters with the system and surroundings being identified. These are the corresponding initial conditions and output for the given conditions. The mu value from lab 2 needed to be altered considerably as it created oscillatory behavior in the graph of velocity over time. This suggested that it was previously calculated incorrectly to a large and unacceptable margin of error. Here are the iterative loops that were used to calculate the velocity and position updates. This computational model might have been made more accurate through correct assumptions from lab 2 and reporting measurements of uncertainty. There were different types of error that may have affected the outcome of this experiment, ranging from observational instrumental to pure blunders, such as dropping the magnet through the tube improperly or not measuring the correct amount of time by using photos, video editing tool to find the timestamps of when the magnet was entering the tube and when it was exiting the tube. There were also potential theoretical and systematic errors, which would result from the magnet making contact with the inside of the tube as it fell through. There were other environmental errors, potentially, such as air resistance and drag, which were not accounted for in the computational model. Now, addressing the what if of this lab's experiment. Now, if the resistivity of the conductor was reduced to 0 or as close as possible, the current's magnitude should increase as the resistance and current were inversely proportional. Thus, the magnitude of the magnetic force should increase and it should fall quickly. And if holes or slots were cut into the tube, these openings would create a reduction in inducing currents, leading it to fall faster rather than slower. So in conclusion, this experiment demonstrated how simulated conditions will often need to be changed in order to properly match the adjustments and reduce the gap between what is observed and those results and predicted outcomes. Thank you for watching.